Hello, and welcome to Minds and Matter. I'm your host, Julian. Thank you for lending me your ears and, more importantly, your time. It's Tuesday, July 29th, 2025. Just after 10 in the morning here in New York City. Through my window, I can see the ordinary magic of a summer day. The sun is high, casting sharp, elongated shadows from the ancient oak trees that dot this landscape. There's a gentle, shimmering haze hanging over the distant fields, a signature of the mid-Atlantic humidity that softens the edges of the world. A cardinal, a flash of impossible red, just darted from a branch. It feels like a specific, singular moment. This moment. Now. And yet, this very patch of land I'm on, the small coordinate in space, has been a silent witness to an unfathomable number of such moments. It felt the tread of the Manahoe people for millennia, their lives governed by the cycles of the seasons and the sun. It heard the ring of axes as colonial settlers cleared the forests. It felt the tremors of the Civil War, with the battlefields of Ball's Bluff and Manassas just a short ride from here, moments of intense, violent transformation that forever scarred the American psyche. It saw the slow, quiet reclamation by nature, followed by the inexorable creep of suburbs and, more recently, the silent, humming monoliths of data centers that now define this region, storing the digital memories of a global civilization. All of those past moments, the silent footfalls, the ringing axes, the cannon fire, the construction cranes, they feel gone, utterly vanished into a silent, inaccessible history. And the moments of tomorrow, next week, next century, they feel equally unreal, unborn, a hazy, shimmering potentiality. We live our lives on this razor's edge, this fleeting, ephemeral instant we call the present, seemingly caught between a past that is immutably fixed and a future that is tantalizingly open. This flow, this invisible current carrying us from what was to what will be, is the most fundamental experience of our existence. It is the water we swim in, so pervasive that we barely notice it until we try to grasp it. And when we do, it slips through our fingers. What, then, is time? The question has haunted humanity since the dawn of consciousness. St. Augustine, in the 4th century, famously wrestled with it in his Confessions. What then is time? If no one asks me, I know. If I wish to explain it to one that asketh, I know not. His frustration is our own. We feel time in our bones, in the aging of our bodies, in the rhythm of our hearts, in the nostalgic ache of memory and the anxious pull of anticipation. It is the subject of our greatest art. From Shakespeare's sonnets raging against devouring time to Proust's monumental effort to recapture lost time through the taste of a Madeleine, to Salvador Dali's surreal, melting clocks, depicting the strange elasticity of our inner experience. We are obsessed with it. We measure it with clocks of astonishing precision, atomic clocks based on the vibrations of cesium atoms, so accurate they would not lose or gain a single second in over 300 million years. We have tethered our global civilization to this precise, unyielding beat. Yet, for all our ability to measure it, its fundamental nature remains the deepest, most obstinate, and most profound mystery in all of science and philosophy. It is the canvas on which the entirety of reality is painted, but what is the canvas itself made of? Is it a real, flowing river, as our intuition screams from the depths of our being? Or is that feeling, the very sense of passage, a grand and powerful illusion constructed by the intricate machinery of our minds, a convenient fiction that allows us to navigate a world that is, at its core, timeless? Today, we are going on an expedition. A deep, exhaustive dive. We are going to put this familiar concept on the examining table and look at it with every tool we have. We will be detectives, historians, and philosophers. We will start in the most intimate of places, our own minds, and explore the strange, subjective, and malleable nature of psychological time. We will listen to the echoes of the ancient Greeks, distinguishing the relentless, quantitative time of clocks, chronos, from the rich, qualitative time of meaningful moments, kairos. We will journey through the intricate neural architecture of the brain, from the master circadian pacemaker in the hypothalamus to the dopamine-fueled clocks that warp our perception of seconds and minutes, trying to understand how this 3-pound universe inside our skulls constructs our sense of duration, memory, and future projection. Then, we will turn to the giants of physics, the great explorers of the cosmos. We will stand in awe of Sir Isaac Newton's majestic vision of a single, absolute, universal time, a great cosmic clockwork ticking equably for all of creation, a concept that dominated science for over 2 centuries. We will feel the first cracks in that perfect foundation appear with the vexing paradoxes of heat and light that emerged in the 19th century. Then, we will sit with a young, unknown Albert Einstein in a Swiss patent office in 1905 and watch as he performs one of the greatest feats of imagination in human history, shattering Newton's clock into a million relative pieces. We will see him weave time into the very fabric of space itself, revealing a dynamic, four-dimensional reality that can be stretched by motion and warped and bent by the gravity of stars and planets. From there, our path will get even stranger, leading us to the absolute frontiers of human knowledge. We will descend into the bewildering realm of the quantum and the cosmic. We will grapple with the stubborn arrow of time, and the startling, revolutionary idea that its relentless forward direction is not a fundamental law of physics, but a mere statistical anomaly, a fluke born from the peculiar, highly ordered, and utterly mysterious state of our universe at the Big Bang. We will confront the master equations of quantum cosmology, where time, as a variable, seems to evaporate completely, suggesting a fundamental layer of reality that is utterly timeless. Finally, we will surface, gasping, into the cold, clear air of philosophy. We will weigh the evidence for a universe where only the fleeting present is real against the mind-bending block universe of eternalism, where the past, present, and future all exist, co-eternally, laid out like a vast, four-dimensional map. And standing within that frozen block of spacetime, we will be forced to ask the ultimate question: what becomes of our most cherished notion, our sense of our own agency, our free will? This will be a journey of dismantling. We will take the clock of reality apart, piece by piece, spring by spring, gear by gear, until we are left staring at its most fundamental components, or perhaps, at the shocking discovery that there are no gears at all. So please, find a comfortable spot. Settle in. The journey will be long, and the terrain, at times, difficult. But I promise you, the view will be worth it. Let us begin. This is Minds and Matter. Part 1, The Intuitive Clock, the Labyrinth of Psychological Time. Before we can dream of the cosmic scale, we must first understand the human scale. All our inquiries into the nature of time begin and end with the experience of it, an experience generated by the staggeringly complex biological machine between our ears. Our internal, subjective sense of time is the source of all our questions, the bedrock of our intuition. And that bedrock, upon closer inspection, is a strange, shifting, and deeply personal landscape. Chronos and Kairos, the two faces of time. The ancient Greeks, with their characteristic philosophical precision, understood that a single word was insufficient to capture the multifaceted nature of time. They gave us two, Chronos and Kairos, a distinction that remains profoundly relevant today. Chronos is the time we are most familiar with, the time of the clock and the calendar. It is sequential, quantitative, and relentlessly linear. It is the time that can be measured, divided, and tracked. The ticking of the second hand, the turning of the day, the marching of the years, this is the domain of Chronos. It is impersonal and utterly indifferent to human affairs. Chronos treats all its intervals as equal. 1 hour is 1 hour, whether it is spent in excruciating boredom or ecstatic joy. It is the time of physics, of spreadsheets, of deadlines, of mortality. It is the framework that contains our lives. Kairos, however, is something else entirely. It is qualitative, not quantitative. It is the time of human experience, of meaning, and of significance. Kairos denotes the opportune moment, the right time, the critical instant where action is decisive and transformative. It is the flash of inspiration for an artist that solves a creative problem. It is the perfect, pregnant pause in a comedian's delivery that makes the punchline land with explosive force. It is the fleeting window of opportunity for a general on the battlefield to turn the tide of a war. For the Christian theologian Paul Tillich, Kairos was the moment of the eternal breaking into the temporal, a moment of revelation or fulfillment. It is the flow state described by the psychologist Mihai Csikszentmihalyi, where an athlete or musician is so completely absorbed in their activity that their sense of self and the passage of time seem to dissolve into pure, effortless action. A 10-minute conversation with a mentor can have such immense kairos that it reorients the entire trajectory of a life, its significance far outweighing its brief duration in chronos. We live our lives within the rigid grid of chronos, but we experience our lives through the emotionally charged, narrative-driven lens of kairos. Understanding the nature of time means understanding this fundamental duality between the time that passes and the time that matters. The brain's orchestra of clocks. How does the brain produce this rich and very temporal experience? For a long time, scientists searched for a single, centralized clock in the brain, a neural equivalent of a computer's quartz crystal. They never found one. Instead, what has emerged is a picture of a highly distributed, decentralized system, an entire orchestra of different timekeeping mechanisms, each specialized for a different timescale and purpose. At the grandest scale, we have our master conductor, the circadian clock. Deep in the brain's hypothalamus, sitting just above the point where the optic nerves cross, is a tiny, paired cluster of about 20,000 neurons called the suprachiasmatic nucleus, or SCN. This is the central hub for the body's myriad of roughly 24-hour rhythms. The SCN is a true biological marvel. It receives direct input from specialized photosensitive cells in the retina of your eyes, allowing it to use the most reliable signal in the environment, the daily cycle of light and dark, to synchronize your internal biology with the external world. The timekeeping mechanism within each SCN neuron is an exquisite molecular feedback loop. A pair of genes, often called clock and MAL1, act as activators. They turn on the production of another pair of genes, period, PR, and cryptochrome, CRY. As the proteins produced by the PR and CRY genes build up in the cell's cytoplasm over the course of the day, they eventually pair up, re-enter the nucleus, and act as inhibitors, shutting down the very clock and MAL1 genes that created them. As these inhibitory proteins degrade overnight, the cycle begins anew. This elegant, self-regulating loop, taking approximately 24 hours to complete, is the molecular basis of our internal day. In 2017, the Nobel Prize in Physiology or Medicine was awarded to Jeffrey Hall, Michael Rosbash, and Michael Young for elucidating these very mechanisms. The SCN then sends out signals, like a conductor waving a baton, to synchronize countless peripheral clocks in our liver, muscles, and other organs, orchestrating our sleep-wake cycles, hormone release, like melatonin and cortisol, core body temperature, and metabolism. This system explains chronotypes, why some of us are larks, morning people, and others are owls, evening people, and why we feel the disorienting effects of jet lag or shift work, a condition of the social jet lag where our internal biology is at war with our external schedule. For shorter durations, on the timescale of seconds to minutes where our conscious experience lives, the brain seems to use different, more flexible systems. One influential theory is the pacemaker accumulator model. It posits a kind of internal stopwatch. A neural pacemaker emits regular pulses, a gate opens and closes to control the flow of these pulses, and an accumulator counts the pulses that get through, with the final count representing the elapsed time. A more recent and neurologically grounded theory is the striatal beat frequency model. It suggests that time is encoded in the patterns of neural activity itself. Large populations of neurons in the cortex are constantly firing in rhythmic, oscillating waves, but at many different frequencies, like a vast collection of drummers all beating at slightly different tempos. The basal ganglia, particularly a deep brain structure called the striatum, is thought to act as a coincidence detector. It is constantly listening for when the beats of specific groups of these cortical drummers happen to align or coincide. The unique pattern of these coincidences over a period creates a neural signature for a specific duration. This model is particularly powerful because it neatly explains how our emotional and chemical state can warp our sense of time. The striatum is a hub for the neurotransmitter dopamine, which is central to motivation, reward, and attention. When something exciting or rewarding happens, your brain gets a surge of dopamine. This dopamine acts like a stimulant on the cortical oscillators, causing them to fire faster. As a result, more beats and coincidences are detected by the striatum within a given interval of objective time. The brain interprets this higher density of neural events as time passing more quickly. This is why time flies when you're having fun. Conversely, in states of boredom, or in neurological conditions characterized by dopamine deficiency like Parkinson's disease, this internal clock slows down. Fewer neural events are registered per second, and time feels like it's dragging on interminably. The malleable past, the imagined future. Our sense of time is inextricably linked with our sense of self, and the faculty that binds them together is memory. The Canadian cognitive neuroscientist Endel Tulving proposed the concept of chronesthesia, literally, time consciousness to describe the brain's remarkable ability to mentally travel in time. This isn't just about knowing facts from the past, it's about the feeling of re-experiencing them. Tulving distinguished between two types of long-term memory. Semantic memory is our memory for facts, concepts, and knowledge about the world, knowing that Paris is the capital of France, or that a bicycle has two wheels. Episodic memory, on the other hand, is the memory of our personal experiences, the episodes of our lives. It's not just knowing you went to Paris, it's the vivid recollection of the sight of the Eiffel Tower, the taste of the croissant, the feeling of the cold wind on your face. It is only episodic memory that gives us the feeling of a personal past. It allows us to project ourselves backward in time and relive a moment. Remarkably, the same neural machinery, centered in regions like the hippocampus and the prefrontal cortex, that allows us to re-experience the past also allows us to imagine the future. This prospection is essentially episodic memory in reverse. We take fragments of our past experiences and recombine them to simulate potential future scenarios. This ability to plan, to weigh future consequences, to set long-term goals, is arguably the pinnacle of human cognition. Our sense of a continuous self, a narrative identity that persists through time, is built upon this constant dialogue between the remembered past and the imagined future. But this system is far from a perfect, high-fidelity recorder. Our perception of events is highly subjective. The oddball effect demonstrates this. If you're shown a sequence of identical images, and then one different oddball image is flashed for the exact same duration, you will consistently perceive the oddball image as having lasted longer. The novelty of the image captures more of your attentional resources, leading to a richer, denser encoding of the experience, which your mind then interprets as a longer duration. This effect goes into overdrive during moments of extreme fear. People who survive life-threatening situations, a car crash, a fall, a violent encounter, frequently report that the event seemed to unfold in slow motion. This isn't a paranormal event, it's a feature of memory. In a state of high alert, the amygdala, the brain's fear center, goes into overdrive, commanding the hippocampus to record everything in the highest possible resolution. It's like your brain's camera suddenly switches from its normal 30 frames per second to 1000 frames per second. When you play that memory back later, it's so packed with detail that it feels stretched out, as if it happened over a much longer period. Your brain didn't slow down time, it just created a much more detailed memory of it. Cultural time, the software of society. Our experience of time isn't just a product of our hardware, our neural circuitry. It is also profoundly shaped by our software, the cultural frameworks we inherit. The anthropologist Edward T. Hall, in the 1950s, distinguished between monochronic and polychronic cultures. Monochronic cultures, typical of North America, Northern Europe, and Japan, see time as a linear, tangible commodity. Time is a road that can be divided into segments, scheduled, and managed. The focus is on efficiency, punctuality, and adhering to plans. Time is money, as Benjamin Franklin famously advised. In this model, interrupting a conversation or being late for a meeting is considered rude because you are stealing someone's valuable time. Polychronic cultures, common in Latin America, the Middle East, and much of sub-Saharan Africa, treat time as much more fluid and multifaceted. The focus is on relationships, completing human transactions, and being involved in multiple things at once. Schedules are flexible, and punctuality is less important than giving a current interaction the time it deserves. Time is seen as serving people, not the other way around. These cultural models have deep historical roots. The linear, progressive view of time that dominates the modern West is a legacy of Judeo-Christian eschatology, with its clear narrative of a beginning, creation, a middle, human history, and an end, the final judgment. This was secularized during the Enlightenment into the idea of progress, the belief that humanity is on an ever-upward trajectory of improvement. This linear model is perfectly suited for the logic of capitalism, which requires standardized time to coordinate labor and production. In stark contrast are the cyclical worldviews prevalent in many Eastern and indigenous traditions. In Hinduism, the universe undergoes endless grand cycles, or yugas. Each cycle is divided into 4 ages, the Satya Yuga, an age of truth, the Treta Yuga, the Dvapara Yuga, and finally the Kali Yuga, our current age of darkness and conflict, after which the universe is destroyed and reborn, starting the cycle anew. Similarly, Buddhist philosophy posits the concept of samsara, the endless cycle of death and rebirth driven by karma, from which one seeks liberation. The Mayan long count calendar, with its intricate cycles within cycles, also reflects a deeply cyclical cosmology. This perspective can foster a different attitude toward life, one less focused on frantic linear progress and more on one's role and duties within an eternal, repeating cosmic pattern. Perhaps one of the most profound and challenging conceptions of time comes from Australian Aboriginal cultures. The concept of the dreaming or dreamtime is not a reference to a past that is gone. It is a timeless, ever-present metaphysical reality where the ancestral spirits and the great events of creation are not in the past but are eternally coexistent with the present landscape. The past is not behind us, it is a parallel dimension that is all around us, accessible through ceremony, songlines, and sacred sites. So, we see that the time of the mind, the only time we ever truly know, is a labyrinth. It is a breathtakingly complex construction of our biology, a dynamic product of our neurochemistry, a narrative woven from the threads of memory, and a perception deeply colored by the lens of our culture. It is personal, it is malleable, and it is powerfully, stubbornly directional. But is this one-way arrow of time, this river that seems to carry us relentlessly forward, merely a feature of our consciousness? Or does it point to a deeper, physical truth about the fabric of the cosmos itself? To answer that, we must leave the familiar warmth and complexity of our inner world and step into the cold, stark, magnificent, and mind-bending universe of physics. Part 2: The Physical Clock, the Warping of Spacetime. For 2 triumphant centuries, the physical world ran on Newton's time. In his monumental Philosophiae Naturalis Principia Mathematica of 1687, Sir Isaac Newton didn't just give us a set of laws for motion and gravity, he gave us a new cosmos. His was a clockwork universe, a majestic, intricate machine created by a divine watchmaker, set in motion, and then left to run according to precise, immutable, and discoverable mathematical laws. This worldview, which became the bedrock of the Enlightenment, was profoundly deterministic. The French mathematician Pierre-Simon Laplace, in the early 19th century, gave this idea its most famous expression in a thought experiment involving a hypothetical vast intellect, which came to be known as Laplace's demon. Laplace argued that if this demon knew the precise location and momentum of every single atom in the universe at one particular instant, it could, by applying Newton's laws, calculate the entire future and the entire past with perfect certainty. In this clockwork view, free will was an illusion, and the future was as fixed and determined as the past. For such a deterministic machine to function, it needed a rigid, absolute framework. Newton provided it. Space, for him, was an infinite, unchanging three-dimensional grid, an invisible, absolute stage on which the cosmic drama played out. And time was its temporal counterpart. He defined it with an authority that brooked no argument. Absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external. Let's dissect this powerful statement. Absolute, true, and mathematical time, this means there is one, and only one, master clock for the entire cosmos. A second on Earth was a second on Jupiter and a second in the most distant, undiscovered galaxy. Flows equably, this means the river of time is perfectly steady, never speeding up or slowing down. Without relation to anything external, this means it is completely independent of the matter and events within it. It is the ultimate, incorruptible background parameter, the metronome of God. This vision was not only intuitive, it was spectacularly successful. Newtonian physics built the modern world. It allowed us to predict the return of comets, calculate the tides, design bridges and engines, and fire artillery with unprecedented precision. For over 200 years, Newton's absolute time was the granite foundation of all physical science. The gathering storm, cracks in the clockwork. By the late 19th century, however, storm clouds were gathering on the horizon of physics. Cracks began to appear in Newton's perfect edifice, coming from 2 different branches of the science. The first was thermodynamics, the science of heat, work, and energy. While Newton's mechanical laws were perfectly time-reversible, a movie of planets orbiting would look just as valid run backwards, the real world of steam engines and chemical reactions was clearly not. The newly formulated second law of thermodynamics, championed by figures like Rudolf Clausius, introduced a fundamental arrow of time into physics. It stated that in any closed, isolated system, a quantity called entropy, a measure of disorder, randomness, or wasted energy, always increases. An egg can scramble, but it can't unscramble. A drop of ink disperses in water, but a cloudy glass of water never spontaneously separates into clear water and a neat drop of ink. This one-way street of thermodynamics suggested a universe that was constantly running down, heading towards a final state of maximum disorder and uniform temperature known as the heat death of the universe. This irreversible decay was profoundly at odds with the perfect, reversible clockwork of Newton. The second, more acute crisis came from the beautiful and powerful theory of electromagnetism. In the 1860s, the Scottish physicist James Clerk Maxwell achieved a stunning unification, showing that electricity, magnetism, and light were all different manifestations of a single underlying phenomenon, the electromagnetic field. His set of 4 elegant equations described the behavior of this field with perfection. But they contained a time bomb. They predicted that light is a self-propagating wave that travels through a vacuum at a very specific speed, c. approximately 300,000 kilometers per second. The bombshell was that this speed was an absolute constant, regardless of the motion of the source or the observer. This was a direct, violent contradiction of Newtonian mechanics and all common sense, a principle known as Galilean relativity. Velocities were supposed to add and subtract. If you are on a train moving at 100 km per hour and throw a ball forward at 20 km per hour, a person on the ground sees the ball moving at 120 km per hour. But if you stood on that train and turned on a flashlight, Maxwell's equations insisted that both you and the person on the ground would measure the speed of that light beam as exactly c. This seemed logically impossible. To save Newton's laws, physicists of the late 19th century proposed the existence of an invisible, space-filling medium, the luminiferous ether. The hypothetical substance through which light waves were thought to propagate, just as sound waves propagate through air. If the ether existed, then the true speed c would be the speed of light relative to this absolute, stationary ether. Our measured speed would then depend on our own motion through the ether, and Newtonian relativity would be saved. The race was on to detect it. This led to one of the most famous and consequential failed experiments in the history of science. In 1887, at what is now Case Western Reserve University, the American physicists Albert Michelson and Edward Morley constructed an ingenious device called an interferometer. The logic was simple but brilliant. They would split a single beam of light, sending the 2 new beams on perpendicular paths of exactly the same length. The beams would then be reflected by mirrors and recombined at a detector. The Earth itself is moving at great speed through space as it orbits the Sun. If the ether existed, the Earth must be moving through it, creating an ether wind. One of the light beams, the one traveling into this wind, should be slowed down and then sped up on its return journey, while the other, traveling cross-stream, would be affected differently. This difference in travel time, though minuscule, should cause the 2 waves to be slightly out of phase when they recombined, creating a predictable shift in their interference pattern. Michelson and Morley mounted their delicate apparatus on a massive block of sandstone floating in a pool of mercury to eliminate vibrations and allow for smooth rotation. They ran the experiment with painstaking care, at different times of day, at different times of year, when the Earth's velocity vector points in different directions. The result was always the same, absolute null. There was no fringe shift. There was no ether wind. In their own words, the results were decidedly negative. The speed of light was stubbornly, paradoxically constant. Physics was broken. Einstein's revolution, the malleability of time. The solution came not from a seasoned professor at a great university, but from a 26-year-old patent clerk in Bern, Switzerland. In 1905, his Annus Mirabilis or Miracle Year, Albert Einstein published a series of papers that would change the course of science forever. In one, titled On the Electrodynamics of Moving Bodies, he proposed a radical solution to the light paradox. Instead of trying to explain away the constancy of the speed of light, he embraced it as a fundamental principle of nature. He started from 2 simple, elegant postulates. The principle of relativity: the laws of physics are the same for all observers in uniform motion. The constancy of the speed of light: the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two seemingly innocuous starting points, Einstein, with impeccable logic, derived the entire theory of special relativity. He realized that if the speed of light must be absolute, then something else must be relative. That something was space and time. His famous thought experiment of the train and the lightning bolts illustrates this with devastating clarity. Imagine Anna is standing in the exact middle of a long, speeding train car. Ben is standing on the station platform as the train rushes by. At the precise moment Anna passes Ben, two powerful lightning bolts strike the train simultaneously, one at the very front of the car and one at the very back. Let's see this from Anna's perspective. Since she is standing perfectly still in the middle of her own reference frame, the train, and the lightning bolt struck the front and back at the same time, the light from each strike has to travel the same distance to reach her eyes. Therefore, she sees the two flashes of light arrive at the exact same moment. She would rightly conclude that the strikes were simultaneous. Now let's see this from Ben's perspective on the platform. He also sees the two lightning strikes occur at the front and back of the train. But during the tiny interval it takes for the light to travel from the strike points to his eyes, the train itself has moved forward. The light from the rear strike has to travel a longer distance to catch up to Ben's position, while the light from the front strike has a shorter distance to cover because the point of the strike is moving away from it. Therefore, Ben sees the flash of light from the front of the train before he sees the flash of light from the back. He would rightly conclude that the strikes were not simultaneous. So who is correct? The Newtonian answer would demand a single, absolute truth. Einstein's revolutionary insight was to declare that they are both correct. Simultaneity is not absolute, it is relative to your frame of reference. There is no universal now that slices across the entire cosmos. And if simultaneity is relative, then the duration of time itself must also be relative. This leads directly to the phenomenon of time dilation. Imagine a light clock on Anna's train, where a photon bounces between two mirrors, one on the floor and one on the ceiling. For Anna, the photon just travels straight up and down. But for Ben on the platform, he sees the train moving, so the photon traces a longer, diagonal path. Since both observers must agree on the speed of light, c, but Ben sees the light travel a longer distance, he must conclude that more time has elapsed. In other words, he sees Anna's clock is ticking more slowly than his own. The faster you move through space, the slower your clock ticks relative to a stationary observer. The effect is quantified by the famous Lorentz factor, gamma, which equals 1 over the square root of 1 minus velocity squared over c squared, where c is the speed of light. As your velocity v approaches the speed of light c, the gamma factor grows towards infinity, and time for you slows to a crawl relative to the outside world. This leads to the famous twin paradox. Imagine two 20-year-old twins, Tara and Astro. Tara stays on Earth. Astro embarks on a journey to a star 10 light-years away in a spaceship that can travel at 99.5% the speed of light, 0.995 c. At this speed, the Lorentz factor gamma is 10. For Tara on Earth, the round trip takes a little over 20 years, 10 years out, 10 years back. When she sees Astro's ship return, she is 40 years old. But for Astro, time has been dilated by a factor of 10. Her shipboard clocks, and her own biological aging, have recorded only 2 years of travel time, 20 years/10. When she steps out of her ship, she is a 22-year-old, meeting her 40-year-old twin sister. She has leaped 18 years into Earth's future. This isn't a paradox, it's a real, physical consequence of the geometry of spacetime, the unified four-dimensional continuum, x, y, z, t, that Einstein's theory revealed. But Einstein wasn't finished. Special relativity only dealt with uniform motion. For another decade, he wrestled with the monumental task of incorporating acceleration and gravity into his new picture. His happiest thought, as he called it, was the principle of equivalence. He realized that the effects of gravity are locally indistinguishable from the effects of acceleration. If you were in a windowless elevator in deep space, accelerating upwards at 9.8 meters per second squared, the feeling would be absolutely identical to standing still on the surface of the Earth. If you dropped a ball, it would fall to the floor in exactly the same way. From this profound insight, Einstein made a monumental leap of logic. Gravity is not a force that pulls things across space, as Newton had conceived it. Gravity is the curvature of spacetime itself, caused by the presence of mass and energy. As the physicist John Archibald Wheeler so elegantly summarized it decades later, spacetime tells matter how to move, matter tells spacetime how to curve. The classic analogy is a bowling ball placed on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. A marble rolled nearby will follow this curve, appearing to be attracted to the bowling ball. Planets orbit the Sun not because of an invisible tether pulling them, but because they are following the straightest possible path, what mathematicians call a geodesic, through the four-dimensional spacetime that has been curved by the Sun's immense mass. And because time is an integral, inseparable part of the spacetime fabric, it means that time, too, is affected by gravity. Clocks tick more slowly in stronger gravitational fields. This is gravitational time dilation. A clock at sea level literally ticks more slowly than a clock on a mountaintop, because it is deeper within Earth's gravitational well. Your feet are aging more slowly than your head. This isn't just a theoretical curiosity, it is a crucial, daily engineering necessity. The Global Positioning System, GPS, in your phone or car relies on a constellation of about 31 satellites orbiting the Earth, each containing a highly accurate atomic clock. These satellites are subject to two relativistic effects. First, due to their high speed relative to us on the ground, about 14,000 km per hour, special relativity predicts their clocks should slow down by about 7 microseconds per day. Second, because they are in a much higher orbit where Earth's gravity is weaker, general relativity predicts their clocks should speed up by about 45 microseconds per day. The net effect is that their clocks run faster than ground-based clocks by about 38 microseconds, 45-7, every single day. It's a tiny amount, but if the GPS engineers didn't constantly correct for this relativistic effect, the entire system would be useless. Positional errors would accumulate at a rate of nearly 10 kilometers every single day. Your ability to navigate to a coffee shop is a daily, practical confirmation of Einstein's warped, relative time. In a single decade, Einstein had utterly demolished the 200-year-old Newtonian paradigm. The universal river was gone, replaced by a multitude of personal streams, all flowing at different rates, all woven into a dynamic fabric that could be bent, twisted, and warped. Time was no longer the absolute stage on which reality performed, it had become one of the lead actors. This was a radical, profoundly strange new reality. But it was still a reality that was smooth and continuous at its heart. What would happen when this strange new vision of time collided with the grainy, discontinuous, and probabilistic world of the quantum? The result would be the deepest and most confounding puzzle in all of modern science. Part 3: The Broken Clock, Entropy and the Quantum Void. The two great triumphs of 20th century physics, general relativity and quantum mechanics, stand like two magnificent, rival empires. Each rules its own domain. General relativity governs the cosmos of the very large, stars, galaxies, black holes, the expansion of the universe, while quantum mechanics governs the subatomic realm of the very small, atoms, electrons, quarks, photons, with breathtaking, unprecedented accuracy. They are, without question, the most successful scientific theories ever conceived. They are also, however, spectacularly, fundamentally incompatible. Their foundational principles, their core assumptions about the nature of reality, are profoundly at odds. And their central point of conflict, the deepest and most fiercely disputed territory between these two empires, is the nature of time itself. Let's clarify the conflict. General relativity, as we've seen, is a background-independent theory. Spacetime is not a fixed stage, it is a dynamic, physical entity that acts on matter and is acted upon by matter. Quantum mechanics, at least in its standard textbook formulation, is background-dependent. It presumes the existence of a fixed, non-dynamical, Newtonian-style spacetime stage on which the bizarre quantum drama unfolds. Furthermore, GR is a local theory. The curvature at one point in spacetime is determined by the mass energy at that point. Quantum mechanics, on the other hand, contains a shocking non-locality, most famously expressed in the phenomenon of entanglement, where two particles can be linked in such a way that measuring a property of one instantaneously influences the property of the other, no matter how far apart they are, what Einstein famously derided as spooky action at a distance. Finally, GR is a deterministic theory. Given initial conditions, the equations specify a single, unique future. Quantum mechanics is fundamentally probabilistic. Its core equation, the Schrödinger equation, describes the evolution of a wave function, which only gives the probabilities of different outcomes upon measurement. This clash of principles becomes a full-blown crisis when we are forced to consider situations where both theories must apply, such as in describing the singularity at the center of a black hole, where immense mass is crushed into a quantum-sized point, or in describing the first instant of the Big Bang, when the entire observable universe was smaller than an atom. To describe these extreme environments, you need a theory of quantum gravity. For nearly a century, this has been the holy grail of theoretical physics. And the primary conceptual obstacle, the dragon guarding this treasure, is the problem of time. When you take the principles of GR, like background independence, and try to apply the rules of quantum mechanics to the space-time fabric itself, a mathematical and philosophical disaster seems to happen. In the most direct attempt to unify the theories, an equation formulated by John Wheeler and Bryce DeWitt in the 1960s, the variable for time, t, simply vanishes from the mathematics. The resulting Wheeler-DeWitt equation, symbolically represented as h caret psi equals 0, is supposed to be the master equation for the quantum state of the entire universe, represented by the wave function, psi. But it is a static equation. It says that the energy of the universe, represented by the Hamiltonian operator h caret is 0. There is no time parameter to describe evolution. It describes a static, frozen, timeless reality. This does not necessarily mean time is an illusion, but it strongly suggests that time as we know it, this flowing, directed experience, is not a fundamental component of reality. It is likely an emergent phenomenon, something that arises from a deeper, timeless reality, much as the properties of a liquid, like wetness and flow, emerge from the collective statistical interactions of trillions of individual H2O molecules that are not themselves liquid. The arrow of entropy. If the fundamental laws are timeless, then where does the most obvious feature of time, its relentless forward direction, the arrow of time, come from? Why do we remember the past and not the future? Why do eggs break but not unbreak? The overwhelming consensus among physicists today is that the answer lies not in the fundamental laws of motion, which are, for the most part, time-symmetric, but in the most powerful statistical law in all of physics, the second law of thermodynamics. The second law, born from the gritty, practical study of steam engines in the 19th century, states that the total entropy, or disorder, of a closed, isolated system, like the universe as a whole, always increases or stays the same. It never decreases. It was the brilliant and tragic Austrian physicist Ludwig Boltzmann who, in the late 19th century, gave us the microscopic, statistical understanding of entropy. He realized it was simply a matter of probability. Any large-scale state of a system, what we call a macrostate, like a room having a certain temperature, corresponds to a huge number of possible arrangements of its constituent atoms, its microstates. Boltzmann showed that entropy is a measure of the number of microstates corresponding to a given macrostate. His famous equation, S equals Clog W, now engraved on his tombstone, links entropy, S, to the number of possible microstates, W, via a constant, K. Consider a box of gas molecules. A low-entropy state would be having all the molecules crowded into one corner. There are relatively few ways for this to happen. A high-entropy state is having the molecules spread out evenly throughout the box. There are a staggering number of ways for the molecules to be arranged in this spread-out configuration. Systems evolve from less probable, low-entropy, ordered states to more probable, high-entropy, disordered states simply because there are vastly more ways to be disordered than to be ordered. It's not that it's physically impossible for all the air molecules in your room to suddenly rush into one corner. It's just so statistically improbable that it would not happen in many lifetimes of the universe. The arrow of time, then, according to this powerful view, is nothing more than the universe's relentless slide towards states of higher probability. It is the arrow of increasing entropy. We remember the past and not the future because the past was a state of lower entropy. The very act of forming a memory, of creating an ordered trace in our brain, is an entropy-increasing process, as the chemical reactions involved release heat and increase the total disorder of the universe. This powerful idea, however, just pushes the ultimate mystery one level deeper. It explains why the arrow points forward from any given moment, but it doesn't explain why there was a backward to point from in the first place. If the universe is always moving towards greater disorder, why wasn't it already in a state of maximum disorder? Why did it begin in a state of such incredible, unnatural, improbable order? This is the great cosmological puzzle of the past hypothesis. The Big Bang, 13.8 billion years ago, was not a chaotic explosion into an existing space. In its earliest moments, it was a state of incredibly high temperature and density, but also of exquisite smoothness and uniformity. In gravitational terms, this uniformity is a state of tremendously low entropy. The natural tendency of gravity is to clump matter together into stars, galaxies, and eventually black holes, which is a much more disordered, higher entropy state. The universe, for some unknown reason, began in a state of pristine, low entropy order. We have no definitive explanation for why. The Oxford physicist Roger Penrose has called this the most profound mystery in all of physics, suggesting it points to a deeper physics, perhaps involving a cyclical cosmology where our Big Bang was the result of the end of a previous aeon. For now, what we can say is that it seems this one special fact about our universe's origin is the ultimate source of the arrow of time. It's like the universe was born as a perfectly wound-up cosmic clock, and the entire subsequent history of the universe, the formation of galaxies, the burning of stars, the evolution of life, the process of thinking and remembering, is the process of this clock uncoiling, of entropy increasing. The thermodynamic arrow of time that governs everything we experience was fired from the bow of the Big Bang. Quantum timelessness and modern ideas. This leaves us with a staggering picture. Time dissolves under the harsh glare of fundamental physics. At the deepest level, as hinted at by the Wheeler-DeWitt equation, reality may be a static, timeless quantum state, a vast, frozen ocean of quantum possibilities. From this timeless substrate, the four-dimensional spacetime of Einstein emerges, like a pattern of ice freezing on the surface of the ocean. And upon this emergent reality, a direction, the arrow of time, is painted, not by a fundamental, dynamical law, but by a statistical fluke, a consequence of our universe's mysteriously ordered birth. Modern attempts to find a theory of quantum gravity grapple with this emergence. Loop quantum gravity, for instance, envisions that spacetime itself is not continuous but is made of discrete, quantized atoms of space, linked together in a network called a spin network. The evolution of these networks creates a spin foam, and from the complex combinatorics of this foam, a smooth, classical spacetime, complete with an emergent time, is thought to arise at large scales. String theory, or its more modern incarnation M-theory, suggests an even stranger picture, where our four-dimensional spacetime might be a holographic projection emerging from a more fundamental, timeless reality existing in a higher number of dimensions. In all these frontier ideas, time is not what it seems. It is not the absolute, fundamental river of our intuition. It is a secondary, derived, and perhaps even illusory concept. This conclusion is the culmination of our journey through physics. It forces us to leave the relatively firm ground of science and venture into the deep, turbulent, and uncharted waters of philosophy. What does it mean for a conscious being, a being of memory and hope, of choice and consequence, to live in such a world? Part 4, The Philosophical Clock, Freedom in a Frozen Universe. Our scientific expedition to the heart of time has left us stranded on a strange and desolate shore. We have dismantled the intricate clockwork of physics only to find that its most fundamental component, the very passage of time, may not be there at all. This forces us to confront the ultimate questions of existence, questions that have been debated by philosophers for millennia, but which are now infused with a new, strange urgency by the discoveries of modern physics. The central debate pits our deepest intuitions against the stark implications of our best theories, a clash between two rival views of reality, presentism and eternalism. Presentism is the philosophy of common sense, the default setting for the human mind. It is the intuitive belief that only the present moment is real. The past is a realm of events that were real, but are now gone forever, existing only as memories or records. The future does not yet exist, it is a realm of pure potentiality, of possibilities waiting to be born. In this view, reality is just this thin, moving sliver of now, constantly coming into being from the void of the future and vanishing into the non-existence of the past. Presentism feels right. It validates our experience of flow and change. Crucially, it gives us an open, unwritten future, a stage for our free will to be a genuine creative force in the universe. However, as intuitive and psychologically comforting as presentism is, it finds itself in a brutal street fight with Einstein's relativity. As we saw, there is no universal, absolute now that all observers can agree on. My slice of the present is different from the slice of the present for someone flying in a jet plane. This relativity of simultaneity poses a devastating problem for presentism. If only the present is real, whose present are we talking about? If an event on a distant star is in my present but in your future, is that event both real, for me, and not yet real, for you, at the same time? This seems to make reality itself dependent on one state of motion, a conclusion that most physicists and philosophers find deeply problematic. This problem has led many thinkers, often reluctantly, to embrace the far more radical, counterintuitive, and unsettling alternative, eternalism. This is more popularly known as the block universe theory. Eternalism takes Einstein's four-dimensional spacetime at face value and follows its implications to their logical conclusion. It claims that the distinction we make between past, present, and future is a subjective illusion of human consciousness. The reality is a static, four-dimensional spacetime block, and every event, the formation of the Earth, the reign of the dinosaurs, the life of Julius Caesar, this very moment as you hear these words, your own death, and the eventual burnout of the last star in the cosmos is just a different coordinate, a different point, on this vast, four-dimensional map. All moments, past, present, and future, are equally real, coexisting eternally. The dinosaurs are not gone, they are simply elsewhere in spacetime, just as London is not gone just because you are currently in New York. In the block universe, the flow of time is a trick of our consciousness. We are like a reader of a novel. The entire story of War and Peace, from the first page to the last, exists simultaneously, bound within the covers of the book. But to make sense of the narrative, we must read it sequentially, one page at a time. This sequential reading creates for us, the readers, the illusion of an unfolding plot, of suspense, of character development, and of dramatic tension. But the end of the story is just as real and there as the beginning, even before we've read it. The block universe is the novel. Our consciousness is the reader, its spotlight moving along the world line of our life, experiencing the already existing pages of spacetime in a particular order. As we noted, Einstein himself was a firm and unapologetic eternalist. His famous letter consoling the family of his lifelong friend, Michel Bessot, upon his death in 1955, is a perfect, poignant expression of this worldview. Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. This is a worldview of immense and chilling grandeur. But its implications for human agency, for our sense of ourselves as authors of our own lives, are severe. If the future is already there in the block, just as real and fixed as the past, what becomes of our most cherished notion, our free will? If my choice tomorrow to have tea instead of coffee is already a fixed, eternally existing feature of the spacetime geometry, in what meaningful sense am I free to choose? This seems to lock us into a rigid determinism, a form of fatalism where we are merely puppets acting out a pre-written, four-dimensional script. We are characters in a book that has already been printed. The philosophical responses to this profound challenge are complex and form a debate that rages to this day. Hard determinists accept this conclusion. They argue that free will is indeed an illusion, a pre-scientific notion incompatible with a physicalist worldview, whether it's a classical or a block universe model. Libertarians, in the philosophical sense, reject this. They argue that free will is real and fundamental, and therefore, any physical theory that denies it must be incomplete. They hold out for a future physics, perhaps one that incorporates a true indeterminacy at the quantum level, that will create space for genuine freedom. Compatibilists try to find a middle ground. They argue that our definition of free will is the problem, and that free will and determinism can coexist. A compatibilist would say that you are free as long as your actions are caused by your own internal deliberations, beliefs, and desires, without external coercion or constraint. The fact that this deliberation is itself a timelessly existing part of the causal chain within the block doesn't negate the fact that it was your deliberation that caused the outcome. The character in the novel still makes choices based on their personality, motivations, and experiences within the story. Their choices are determined by the story's logic, but from their perspective, they are making them. Whether this redefinition of freedom satisfies you is, of course, a deep and personal philosophical question. Some philosophers have tried to find hybrid models. The growing block universe theory, for instance, suggests that the past and the present are real, but the future is not. Reality is a block that is constantly growing as the present moment accretes new layers of spacetime into being. This preserves an open future but has its own problems, such as defining whose present is the special edge where reality is being created. The block universe, if true, does offer a strange sort of metaphysical solace. It suggests a kind of conservation of moments. No experience is ever truly annihilated by the passage of time. Every joy you have ever experienced, every moment of profound love, every beautiful sunset you have ever witnessed, every conversation that has shaped who you are. These things are not lost to a non-existent past. They remain as permanent features of the four-dimensional cosmic landscape. The past is not a graveyard of dead moments. It is a timeless country to which we can never return, but which will always, in a very real and physical sense, be. So we are left with a profound schism, a Grand Canyon between the world as it is experienced by a conscious human being and the world as it seems to be described by our most fundamental physics. The time of our minds, the personal, flowing, dynamic time of Kairos, is a reality of change, of becoming, of narrative. The time of physics, the impersonal, static, geometric time of Chronos, seems to be a reality of pure, unchanging, eternal being. Reconciling these two views is perhaps the greatest unfinished task of science and philosophy. Perhaps our consciousness, by its very nature as a predictive machine built from the raw material of memory, can do nothing but perceive a timeless reality as a temporal flow. The illusion of passage may be the necessary price we pay for the gift of self-awareness. Host, our expedition, for today, has reached its end. We began on a simple Tuesday morning in New York, with the immediate, undeniable feeling of the present moment. We have journeyed from there to the very foundations of reality and back, a round trip through the strangest territories of the human mind and the cosmos. We saw how our brains are not simple clocks but brilliant, masterful artists, painting a rich, subjective, emotional, and culturally shaded portrait of time. We learned that this portrait is unique to each of us, warped by our attention, colored by our emotions, and framed by the stories our culture tells us. We then watched the majestic, absolute clockwork of Newton, a vision of perfect, universal time that reigned for over 2 centuries, be dismantled by the quiet genius of Einstein. We saw its universal river shatter into a million personal streams, and we learned that time itself is a physical, malleable thing, woven into the very fabric of spacetime, a fabric that can be stretched by speed and bent by the gravity of stars. We descended further, into the bewildering quantum realm, where the familiar arrow of time, pointing us from past to future, revealed itself not as a fundamental law, but as a mere statistical quirk, a consequence of our universe's strange, unexplained, and highly ordered beginning. We stared into the abyss of the Wheeler-DeWitt equation and saw a vision of a fundamental reality where time itself may not exist at all. And from this abyss of timelessness, we emerged to face the profound philosophical fallout. The choice between a fleeting, real present and an eternal, frozen block of spacetime. We confronted the ultimate human question of what it means to be free in a universe that may, in its entirety, already be written. The story, of course, is not finished. It is being written today, in labs where particles are smashed together, on blackboards covered in elegant equations, in brain scanners mapping the flow of thought, and in the quiet contemplation of philosophers around the world. But for now, we are left in a state of profound, humbling, and I think, beautiful awe. Time is at once our most intimate companion and our greatest stranger. It is the engine of all change and the eternal canvas on which all that is unchanging is drawn. It is the source of our deepest anxieties about loss, mortality, and regret, and the wellspring of our greatest hopes for growth, redemption, and the future. So the next time you glance at a clock, or feel a precious moment slip through your fingers, or find yourself lost in a memory of a time long past, or dream of a future yet to come, perhaps you will pause. And you will feel the immense we.